So yeah, welcome to this week's JQI seminar. It's our pleasure to have Chris Laumann visit us from Boston University to tell us about the structure of quantum spin ice. So Chris got his PhD from Princeton 2010, and then he went to Harvard as a postdoc, and that's where I met him. We spent a few nice years together, and then then Chris got Chris was at Perimeter after that for a year, and then a couple of months, okay, and then he got a job at UW, where he was for a few years, and then since 2016 he's been at VU, and since then he's gotten tenure and done well. One of the interesting things about Chris is, this quantum spin ice is going to be one of his more material side of his work, but his work spans from quantum information, including the word quantum satisfiability, something which I know almost nothing about, appears in a lot of his titles. So with that, I'll let Chris take it over.
All right. Well, thank you, everybody. Thank you for coming. It's fun to come and is that mic good? Zoom.
Sounds great. Thanks.
Okay. So
one quick announcement. In case, if you want to talk to Chris, there are plenty of slots available tomorrow on his schedule. So just email me, take out at UNC or Alicia, and then we can talk about it.
Great. Right. Well, thank you. Thank you for inviting me. Thank you all for coming to hear me talk about spin ice. This is a somewhat more materials or condensed matter-y topic for me. I've also thought about a lot of other things that go on around here. I hope that this talk is accessible to the range of the JQI, CMT, various people who I think are in this room, but please feel free to stop me and ask questions at any point. I've put a lot in the talk, and if I don't get through the last topic, I'm not going to cry. If people get more out of it that way, that's fine. Okay. So anyway, this is work. I've been working on quantum spin ice for the last few years. You can see my first foray into the area, published foray into the area is just from 2 years ago. And it's with a variety of collaborators on those 3 projects, some of them overlapping. So many of you will know Frank Wilczek, Roderick Mersner, who's the director of the Max Planck in Dresden, Claudio Castelnuovo is faculty at Cambridge, Sid Moramputi is my former postdoc. He's now a postdoc at MIT. And this is really weird. This like pitch yaw fake laser pointer thing. Sorry. Okay. I apologize if I do strange things with the laser pointer. And then Sal Pace, who did his senior thesis with me as an undergraduate at BU, went to Cambridge for a year where he worked with Claudio, and that's where the last topic here on axions was done, and now he's started as a graduate student at MIT. Okay, so let's start with like not condensed matter. This is like real physics, just for a moment. Okay, so the fine structure constant, what is it? To remind you, there's a few ingredients. So first, Dirac told us there's an elementary charge, E. Okay, maybe it's E over 3 if you believe in QCD, but E, it's an elementary unit of charge, okay? Coulomb, much earlier, told us that the interaction potential energy between the 2 charges is E squared over R, where R is a separation. Planck and Einstein gave us HBAR, Planck's constant, and the speed of light. If you take their product, it is, I'm echoing, it is an energy length. And if you look at Coulomb's law, which is an energy, you see that E squared is also an energy length, okay? And so you can form a ratio, and that goes by the name alpha. It's the fine structure constant. It's a dimensionless measure of the elementary charge in quantum electrodynamics. Why quantum well, there's an HBAR. Okay, but another way to think of this is it's the ratio between the energy of two charges, elementary charges at distance, say a meter, to the energy of a photon with a wavelength of a meter. Okay, and only in the 3+1 dimensional universe we live in is that a dimensionless quantity. Okay, so in this world, the fine structure constant is actually a dimensionless number which characterizes how strong the interactions are in quantum electrodynamics. Okay, in other dimensions, it's not dimensionless. This wouldn't, the distance between the electrons wouldn't drop out. Okay.
So this is all very elementary, but I guess you're counting.
Huh.
These are, of course, not quite correct statements, right? E actually changes, alpha actually changes, and so on.
Yes.
Is that something that's going to be part of your talk, or should I just put that out of my mind completely?
We can
RG flow I'm talking about.
RG, yeah, no, I agree. So you are welcome to come back to it. It is certainly important in the background of my talk, but I'm not.
I'm obsessed with that already, completely. So that's why.
Okay, yeah, no, there is no RG calculation in this talk, but it is certainly in the background. One of the things we did is tried to measure what alpha is in an actual model.
I'm obsessed with the fact that QE actually is ill-defined and doesn't exist. And but in any case, you will come back to that as well. Good, thanks.
Okay, yeah, we can talk about whether it exists or not later. That sounds like a fun discussion. Okay, actually, that's even better. It means whatever I say is correct if it doesn't exist. So now you guys don't have to worry about whether I'm pulling your chain or not. Oh yeah, that's way too small for me. Okay, so the fine structure of the universe. So alpha is of order 1/137. We've known it a long time. That's a small dimensionless number. It could have been 1. Nobody really knows why it's this, why it's around 1/137. It has many consequences that it is this small number. I, as a faculty member who taught, the first course I taught when I got my first job was actually electromagnetism. And it occurred to me that the reason we teach electromagnetism as a course is because this number is small. If it was very big, it would be hard to decouple electromagnetism from everything else. And so we wouldn't be able to separate it into its own course. It wouldn't have been the way we learned how to do physics. Maybe more in this context, small light matter interactions, weak photon-photon scattering, which is via virtual interactions with the matter. The original sort of big play of quantum electrodynamics was that you could get the anomalous magnetic moment of the electron, which the leading order is basically given by this fine structure constant. There's a beautiful argument, I think due to Feynman originally, about the maximum stable element in the periodic table has an atomic number of roughly 1/alpha, which just comes from thinking about quantizing an orbit in a Bohr model of the atom and saying that it can't go faster than the speed of light and sort of doing some comparisons. And you see that the maximum stable element with an orbit that wouldn't just sort of turn into a black hole is given by 1/alpha. And that actually works. The periodic table is about that long. So another thing to think about, if this was much bigger, we wouldn't exist. There'd only be 10 elements, right? No chemistry. Okay, so there's lots of consequences. Nobody really knows where this number comes from. In fact, Wolfgang Pauli, there's this great quote, said, "When I die, my first question to the devil will be, what is the meaning of the fine structure constant?" Yeah, that's right. Okay, so of course, in condensed matter and modern quantum optics, we know that there's many alternate universes which we can create either in synthetic systems like Rydberg arrays, ultra-cold atoms, or in the more sort of material side, we talk about emergent gauge theories coming from interacting spins, or well, frustrated magnetism is the context here. And so I just wanted to throw a few very recent examples of that up. Everything about the fine structure constant, which I said, is really that there is a coupling in electromagnetism, or U1 gauge theory, in 3+1 dimensions, which is this fine structure constant. But people are trying to build other gauge theories. So here are 2 very recent papers about it. There's Rydberg atom array from the Lukin group, where they've done various measurements that suggest they're realizing a state which looks like the ground state of a Z2 gauge theory in 2D, and a similar and similarly timed result coming from the Google group in their Sycamore processor. These are all these synthetic examples. There are other ones that I'm just sort of selecting because these have been very recent, of people trying to build gauge theories in simulators in 1D and 2D. Nobody's trying, as far as I know, to build them in 3D in synthetic type systems yet. In condensed matter, actually, 3D systems are not as hard to come by. Most blocks of crap are 3D. So the main world where we're going to live in this talk is actually in a class of materials which are frustrated magnets called pyrochlores. They're minerals. That's actually a picture of one of them, which have this lattice of atoms on the inside. I'll talk more about it later. And the idea is that they realize a 3+1D U1 gauge theory, which is just like, not just like, but has many analogies to the quantum electrodynamics that we live in, and has fine structure constant. It has a coupling. So anyway, that's that allows us to imagine moving away from alpha being 1/137 and explore other properties of what a QED could look like with, say, a stronger coupling. Okay. Okay. So the plan for the talk is first to explain that last statement I made, that, you know, how do we get from frustrated spins in a pyrochlore lattice to quantum electrodynamics? That's sort of background. Then I can address the question, how big is alpha? The result is on the slide there, in these quantum spin ice type materials, the pyrochlore materials. That's a surprisingly recent new, computed result from our group, in the sense that people have been studying these, the theorists have been studying these models for 10, 15 years, and actually nobody had computed it before. And then I'll talk a little bit about what some of the observable dynamical consequences are of having relatively large interactions in quantum spin ice. And if there's time, then I'll mention, or at least advertise, our most recent work, which is about how if you have certain kinds of coexisting magnetic orders with your quantum spin ice type electrodynamics, you can get things that look like axions, and you can actually study axions coupled to this electromagnetism, all in your material chunk of stuff. Okay, that's the plan. So let's start at the beginning. I feel like it's obligatory for anybody giving a talk like this to put up a slide when they want to talk about frustrated magnets, which has a picture of a triangle with 3 arrows, and you say, this is antiferromagnetic, and then I put this up, and this is down, and this is down, but then wait, what should this be? And I actually think that what the principle of frustration really is in condensed matter physics is this. It's that if spins can't agree on a simple order, like on that triangle, then maybe they'll realize an exotic one. And that's actually what's motivated a lot of frustrated magnetism theory, at the very least.
So it's just completely wrong, because you can have 120 antiferromagnet in the plane. That's what actually happens in the.
Well, that's right. So as always, so that's why I prefer this principle.
People say these things all the time, and just when you know there's a ground state which is perfectly ordered.
There is.
And which happens all the time.
Which happens all the time. That's right. So here I'm going to show you an example of a class of systems where, these pyrochlores, where at least in the model, they don't just order in a simple way. They do realize this exotic emergent gauge theory. Though experimentally, whether they do that is still an open question. And some of the materials we know don't, and some of the materials are still candidates. So
neutron scattering experiments have not been able to bring down the ordering at all. I know nothing about these materials. It's a real question.
Well, give me 2 slides, and then I'll. Okay. So The class of materials broadly are these. They're called the rare earth pyrochlore magnets. What are they? Well, most of them look like this. They have a magnetic ion, which is one of these blue guys from the periodic table. There's a non-magnetic atom as well, which is one of the red guys in the periodic table. There's a bunch of oxygens, which from my point of view are just hanging out to help support the structure. And actually that's also true of these non-magnetic atoms. The picture you see here is of the lattice of the blue atoms. This is a pyrochlore lattice. It has corner sharing tetrahedra. And the red atoms, which actually form an interpenetrating pyrochlore lattice. Okay. This is really complicated to look at. Luckily, we don't have to. We can forget about the red lattice and just think about the one pyrochlore, because that's where all the magnetic moments are that are relevant. Now, you saw, actually, let me go back. I keep hitting the wrong button. There's lots of potential materials here, and indeed, there's lots of different materials that are in this class, and which have different microscopic Hamiltonians and end up having different energy scales, orderings, et cetera. Only some of them are sort of in the regime of being what I want to talk about. There are two particularly well-studied, well-established materials, holmium titanate and dysprosium titanate, which realize what's called classical spin ice, and which I will mention as we're explaining how quantum spin ice arises. We'll go past classical spin ice on the way, so I'll explain what that means. In intermediate temperature regime. And you could view them as actually in some ways one of the best established examples of 3D emergent gauge theory fractionalization, but it's in a classical limit. It's not quantum. Okay, so it's a classical spin liquid if you want, and you'll see what I mean by that in a few minutes. But these order at lower temperature. Okay, so they do exactly what you suggested, Shankar, which is that they instead of staying in sort of these degenerate, frustrated states, exotic states, once you get a low enough temperature, they just find a simple ground state, okay, an ordered state. Then there's a bunch of other candidate quantum spin ices, which sort of go through fads over a few years. People will synthesize them and start doing different kinds of experiments on them and say, oh, we can't see ordering, and we're going to lower and lower temperature, and there's this sort of evidence that maybe they don't order at a low temperature, maybe they remain these quantum, this sort of ideal quantum spin ice. I think the jury's out. Some of these are not really great, I keep hitting the wrong button, not really great candidates anymore. Some of them are still open. I personally couldn't tell you what the exact status of each of those abbreviations is. I'd have to go and look it up because I haven't stored that information in my head. So, okay, good. Does that answer your question?
Yeah.
Yeah, okay.
I already thought it's very complicated, and it changes, and
that's right. That's exactly right. Oh, yeah.
So I guess the first element. Okay, my question is going to be basically: is magnetic anisotropy a significant story in understanding these materials? Like, are these Heisenberg magnets, or are they?
Okay, so.
Okay.
Okay. So here's how to understand these materials, at least if you want to be a theorist like me. Okay. Which means that I don't remember which atom these little circles represent. Okay. What we imagine is that on one of those pyrochlores, so these are pyrochlore lattices, these corner sharing tetrahedra. By the way, is there anybody in here who works with NVs? No? Has ever worked with NVs? Does anybody like diamonds? Has anybody ever bought a diamond ring for somebody? Ever looked? Okay, so maybe it's not helpful, but I actually find this very helpful. This lattice, if you drew the midpoints of all these tetrahedra and drew a line between them, is the diamond lattice. Okay, so if you're used to the diamond lattice, this is easier to visualize. And if you're not, then think of corner sharing tetrahedra. Okay, now at each of the corners, oh my gosh, there's one. There's an atom. It has got a spin on it. It is a 2-level easy axis spin in the simplest examples of these materials, which lives right there. Okay, so easy axis. That means it prefers to point either along this 1-1-1 direction or opposed to it. Okay, there's a strong crystal field anisotropy. Okay, not Heisenberg. That energy scale is actually quite large in most of these materials. It really is a strong crystal field. Okay, and here's the way to start understanding spin ice. This is the simplest toy. Imagine that then the coupling between the atoms is SZ between all neighbors on all tetrahedra. Okay, now what does SZ mean? I'm saying at each of these atoms, I'm picking the Z, I'm defining the Z direction to be the direction along that 1-1-1 relevant 1-1-1 axis. Okay, so SZ means something different at this arrow than at this one. It means in or out. Okay, okay, but now because you know, all of the 4 atoms on each tetrahedron are talking to each other, I can trivially rewrite this. I can say, well, let me rewrite that as a sum over the tetrahedra, sum of the SZ component of the spin on each tetrahedra squared, because it's all coupled within each tetrahedron. Okay.
So what distinguishes up from down?
So actually, there's 2 kinds of tetrahedra. There's, say, up pointing and down pointing, okay, which is the same as a diamond lattice having an A and a B site. So there's A and B tetrahedra, and I define SZ as +1 to point from A to B. Then that uniquely specifies everything. Okay, so that's great, actually, because now look at this. Now I know how to minimize it, right? I have 4 spins in that sum. They're plus or minus a half each. I minimize it by, assuming J is greater than 0, by setting 2 of them to be plus, 2 of them to be minus, which means 2 of them are in, 2 of them are out. Okay, I can be a little bit fancier by saying that that's actually the same as the lattice divergence. It's adding up how much spin is pointing out of each tetrahedron, and I'm squaring it. And this is, the ground states are the 2 and 2 out states, which are divergence-free states of these arrow configurations of the spins. Okay, cool. There are many states which have that property. Here, let me show you. That one also has that property. That one also has that property. Okay, so in fact, the reason these are called ice states, even though this is a spin system that has nothing to do with water, is because this 2 and 2 out rule is the same rule that Bernal and Fowler in 1933 pointed out governs how hydrogen bonding works in water ice. And 2 years after that, Linus Pauling estimated the number of ice states, that is, states that satisfy this 2 and 2 out rule. And it's a very simple estimate, so I feel like it's worth sort of taking you through it. It's pretty easy. For each tetrahedron, there are 4 spins, and there are 4 choose 2 ways to arrange the 2 pointing in and the 2 pointing out. That's 6. So that's 6 to the number of tetrahedra states. But then the neighboring tetrahedra have to agree. And if you randomly picked a 2 and 2 out state on this one and a 2 and 2 out state on that one, they would only agree with a probability of half. And so the number of bonds that sort of cut that down, constraints you have, is a half to the 2n. Okay, and so you take a log and you get an entropy. So there's actually an exponentially large number of ground states of this toy model. Okay, this is the ice entropy. It was measured calorimetrically in water ice a couple years after 1935. And this estimate, which is, that's it, that's the whole estimate. I just gave it to you, right? Was good to something like 1%. Okay. So what is a spinon? Well, what happens if I have a defect in the ice rule? So you can look, these arrows I've drawn satisfy 2 and 2 out. Let me flip that central red arrow. Flip. Now, one of those, this one, has 3 spins pointing in, and this one has 3 spins pointing out. Okay, so that's a defect in the ice rule. I can define a charge to be the divergence of that spin field, and that means that 3 in is this blue guy with a minus sign, and 3 out is this guy with a plus sign. Those are the defects in the ice rule. Those are the spinons. Why do I give them a name rather than just saying, okay, I flipped a spin and I've violated something? Well, I can separate them. let me flip that blue spin. Look, I just healed the defect here, and this guy moved over here. And if you think back to our energy function, actually that didn't cost any energy because I'm only paying energy for where the spinons are. So they freely separate, okay? So this is classical fractionalization. And this is actually almost everything you need to know to be able to understand the classical spin ice materials, that they can be understood naturally in terms of essentially a plasma of plus and minus spinons in an ice background. Okay, cool. Okay. Now, what about if we actually go to zero temperature and sort of want to go quantum? We're at JQI, we got to go quantum. HBAR is 1, man, right? So, what happens? So, first of all, this term here that we started with, that was diagonal. Though this is just literally degeneracy. Here's energy. There's this ice manifold, which has entropically many, exponentially many states. And then there's a big gap to creating those spin-on, anti-spin-on pairs, right? Now, to lift that degeneracy, you need to do something off diagonal. You do many things. The simplest thing you can do, which is sort of consistent with time reversal and various other symmetries, is write a term over nearest neighbors, which does this S plus S minus. Other terms are allowed. This is the simplest to think about. Okay, but this term creates a spin-on anti-spin-on pair. Yeah.
Well, if these were spin a half, then it was right. Yes, these were spin a half, because otherwise S plus minus breaks your basic rule of two-state spins. Like if this,
well, these are S plus and S minus on different. Oh yeah, sure. 2 levels. You can think of more complicated versions of this story.
But the problem with 2 levels is that they don't have spin a half does not have anisotropy terms, so it has to be more.
Yeah. So they're not literally spin half. Actually, in most of these compounds, the spin is something like 7 halves, 5 halves, and the crystal field splitting, it leads you to something like a plus 7 halves to minus 7 halves doublet. And what I mean by this is the operator that moves you around that doublet.
Okay, yeah. So it's not actual.
Which is why I called them 2 level and not spin half.
Right.
Okay. I didn't want to take everybody through all the analysis of those microscopics. That's all. But yes, 2 level is right. And in fact, even in that, there are different versions depending if it's spin half, if it's even or if it's integer, half integer spin, Kramer's, et cetera. There's actually variations in the microscopics that matter. I'm giving you the simplest story. Okay. Okay, good. So this would create a spin-on anti-spin-on pair. And that, of course, would take you out of the ice manifold. But what you can ask is, well, if this is weak, can I do, say, degenerate perturbation theory and figure out what's the lowest order thing that will happen inside this manifold to split the degeneracy? Okay. And the answer is that, well, you could basically, this thing flips 2 spins that are end to end. So it creates a pair, which are 2 tetrahedra apart. And on that pyrochlore lattice, I'm sorry, I don't have a picture of it, the shortest loop actually has length 6. And so if I do this 3 times, I can create them and then hop one of them around and re-annihilate it and go back into the ice manifold. And that, if you think about it, is a ring exchange. Basically, I'm reversing all the spins that are pointing end to end on a loop of length 6 in that manifold, in that lattice. And so here's the effective ring exchange Hamiltonian, which is the leading order thing that can survive if I want to stay in the ice manifold. Okay. Great. So what does it do? Well, there's various ways to sort of motivate what it does, that ring exchange Hamiltonian. This is the one to make it look most familiar, though it's kind of a dirty technical trick, but it's not that dirty, so it's okay. So let's soften that S is half, that SZ is plus or minus half, using a representation with rotors. So I'm going to say that the SZ value is like the angular momentum of a rotor, which could in principle be any integer. And I'm calling it twisted because I'm going to put a twisted boundary condition on it. So it's any integer plus a half. And then the conjugate momentum, little a, if I form this e to the plus or minus IA, will raise or lower that angular momentum. And so using this representation, I can just literally rewrite that Hamiltonian like this. Okay, so what I've done is I've introduced an E squared term. This I put in by hand, this gamma. And that ring exchange term is exactly rewritten as the cosine of a lattice curl of this little A field. Okay, it's basically those S plus S minuses. And I wrote it this way on purpose because it's supposed to make it look sort of like E squared plus B squared, right? Remember, B is curl A. That one I think everybody knows. Okay, good. So in fact, you can see it immediately. If you have small gamma and you therefore have large fluctuations of E, which is like position, and small fluctuations of A, which is the momentum, you can expand the cosine, and you'll get E squared plus B squared. Okay. But remember, what did I do? I softened my S's half constraint. To recover the S's half, I need to take gamma to infinity, right? So that I don't actually use anything except for E is plus or minus a half. And so this argument is a little suspect. And nonetheless, it's actually helpful because it gives you morally the right answer, which was shown by a number of these papers from now 15 years ago. Numerically, that ring exchange model actually actually has emergent photons. So at low energy, what happened is that you lifted that ice degeneracy, and now you have a essentially unique ground state, but there is a pair of linearly dispersing transverse modes, which are actually sort of ring exchange like excitations. They're propagating spin ring exchange things. They're kind of hard to visualize, but the main point is that the effective theory is described by this E squared plus B squared with the constraint, which we've sort of sent all the defects, all the charges away to infinity just to go down to the ring exchange model at all. So we're imposing a Gauss law. We're imposing that the divergence of this electric field is zero, or living on the E charges.
Can you say numerics? What kind of numerics are these? I mean, I just want to get a sense of how reliable it is. How much should we trust it?
At this point, there's been a lot of numerics on it, so you can do it. And I've, as you'll see in a minute, we redid some of this with constrained ED, but which was also done earlier. But there's a bunch of quantum Monte Carlo actually with the right sign of G. There's no sign problem. And so what you look for is evidence of linearly dispersing modes, gapless modes. Now, I'll just point out while we're here, I drew three quasi-particles that are in this effective theory. So the photon is the thing which is coming from sort of just E squared plus B squared. This is actually a compact U1 gauge theory, and so there should be monopoles as well. I call them little a photon, little b monopole to remind you that it's a monopole or a source of the curl of little a, which is this b. And then there's a spinon, which was the thing with the big gap because that was the original energy scale that I then perturbed was JZZ, which is the charge in this theory. So the E charge, okay? And I'm using lowercase a, b, and e to remind you that these are not the real electromagnetic field, which matters if you think about how you're going to start doing experiments on this, because there is a real electromagnetic field, right? This is an internal emergent thing that acts a lot like an electromagnetic field, but it is not the external one.
So suppose I do not want to, I'm not thinking about one gauge theory deep, but I'm a very, very smart condensed matter theorist. I don't want to use that language. So is this photon some kind of spin wave?
It's a transverse spin wave. So the yeah, the
just like the transverse photon, there could be transverse spin, right?
That's right. So it is the main point is that the spin as the SZ component of the spin is divergence free. So these waves have that property, right? And that's yeah. So it is and there's no average value for it either. So the average of SZ is 0. There's fluctuations around that. And those are kind of ring exchange like things because they can't produce divergence as they propagate.
The ring exchange to produce them.
That's right.
But in the end, if I think of them as connected transverse spin wave, that's not an incorrect statement. That's not an incorrect statement.
That's not an incorrect statement. If you don't want to call them photons, you can call them. Yeah, that's fine. That's fine. That's fine.
But there is expectation of S is 0, right?
Yeah.
Yeah, it's all fluctuations.
So
It's all fluctuating.
yeah, so it's not fluctuations around the ferromagnetic state.
That's right. So it's some kind of, that's what I said, spillway with important iteration.
Yeah, that's right.
Yeah.
Yeah,
It's a
yeah,
collective mode. That's how I'm using.
Right.
yeah, yeah. So actually, I'll tell you.
It's not regular field. I understand that.
That's right. So I will say the language around this field is a mess. Okay. So why? So if you are a gauge theorist who gets into it, a lattice gauge theorist or otherwise, you like using the photons and monopoles and charges. It sounds exciting. If you came from classical spin ice, people actually called what I called a spinon here as an E charge, is often called a magnetic monopole in that literature because it's a divergence of M. It's a divergence of the magnetization. Okay. So the little e charge is a big M monopole. Okay. And if you really hate all this fancy language and you want to call it a quotation marks transverse spin wave, I suppose you could do that as well.
It's not very fancy. It was completely understood in 1948.
Right. Well, there's wrinkles here which are neat. No, that's okay. That's okay.
No, but maybe another. So there is gauge. So there are less degrees of A is a vector potential is a gauge dependent degree of freedom. Right? Is that somehow gonna?
So I've actually, if you look at this, I didn't introduce any extra Hilbert space here at the lattice level, right? So this little a is not redundant. It's a phase, right?
There's a difference. Right?
Well, the main point is that I haven't written this in. No, that it just has to do with how you are enforcing the divergence-free constraint.
Sure.
And that's all. So you can write it with extra degrees of freedom by introducing something like a gauge redundancy, et cetera. But I haven't done it.
But you can couple to A in principle.
You can.
Like without break, I can break gauge invariance.
No, you can write S e to the IA. So the thing is that I don't have if I did that though, I would change the electric field and I would do it in a way that produced divergence. So it'd take me out of the ice manifold, right? So if I want to write a more complete lattice gauge theory, which this doesn't have any matter in it. So if I want to introduce matter degrees of freedom and I want them to be like fields I write as charges that move around, then I have to introduce a constraint between them. And then I will start needing to be careful about what I'm allowed to write. So it's a little bit like the Kitaev representation of the toric code as opposed to the gauge theorist representation of the toric code, where you introduce extra degrees of freedom on the sites to indicate where E charges are, right? So this doesn't have extra degrees of freedom in that sense. Okay, but it's.
Can I ask another question?
Yeah.
This is Phil Phillips, and I apologize. I've been missing some of the discussion because not everything from the audience is audible.
Oh, I'm sorry. I should be repeating it.
But anyway, I think I've followed enough of it. What I'm wondering is this like electromagnetism in the sense that accelerated charges produce radiation fields?
Yes, I think so. If you can accelerate the spinon. And in fact, that's an important element of what I'll talk about in a little bit. Or
okay,
producing radiation from moving spinons is definitely going to be relevant to what I'll tell you in a few minutes.
Okay, but accelerating spinons, right?
Yes. Well, for me, they're going to be spinons going faster than the speed of light, so it'll be Cherenkov.
Oh,
I haven't thought too much about how to accelerate them.
Yeah, so I'm thinking of classical electrodynamics. I mean, not that Cherenkov radiation isn't classical, but
yeah. So, but they certainly can radiate, and
okay.
They do. If you wiggle them around, they'll radiate.
Okay. Okay. And is there a similar thing for currents?
Yeah. I mean, all of the mathematical structure is the same as the Maxwell theory.
Okay.
So the same should happen, but the physics interpretation is different because it's in spins and so on, right?
Okay, but now do you have both analogs of both electric and magnetic monopoles?
Yes. So that is one big difference. You can see I have magnetic monopoles, and in fact, the gap to the magnetic monopole is smaller than the gap to the electric charge. Whereas in our universe, as far as we know, if they're magnetic monopoles, they're very, very heavy.
Yeah.
So here they're actually much lighter.
So physically, what are magnetic monopoles? I think I see what electric monopoles are, but what are magnetic monopoles physically?
They are, there's various answers. So of course, what they mean is that there is some place in your spin ice where the effect, if you drew a sphere around it and you measured how much little b flux was coming out, you would find that there was little b flux coming out. Now, what is little b flux? Little b flux has to do with the phase between the say clockwise and counterclockwise superposition in the ground around each ring of arrows, spins pointing this way and spins pointing that way. So now, is that a physics answer? That depends on your taste.
It's a little bit more abstract than saying that the spinons are like electric charge.
That's right, it is. And it's not so obvious how to measure this emergent little b, the magnetic field, directly.
Does this give us insight as to why we don't have magnetic monopoles in the real world?
Oh, I don't think so. I don't think it does. Yeah.
I think we probably have to move on.
Yeah. Let me keep going. Let me keep going. I'm not actually keeping an eye on the time at all. Okay. So I hopefully have motivated or convinced many of you that the effective description of that model, at least, is like QED. There's spinons. It's QED with magnetic monopoles. It has some slightly strange kinematics, but there's a photon. There's charges. It raises a question, or at least I want to raise a question: how big is the coupling? How strongly do those charges interact? Okay. I'm going to zoom in on just this photon bit and say that there's essentially two parameters for the theory of these photons. One of them is the speed of light, and the other one is the fine structure constant. So I've written it in a slightly unusual normalization just to make that coupling appear in the Lagrangian. Okay, so you can see it's there, right? Normally we absorb it into an E that shows up in how it couples to fields. But if you rescale fields, you can make it pop out. Okay, so what do we actually have? So my claim is that we had this Maxwell theory as the emergent description, but what we actually had was this microscopic lattice rotor thing. And how do we get from this to this long wavelength description with these two parameters? Well, one approach, we go back and say, well, for small gamma, like I said before, we expand the cosine, and then you can, it's a few lines of algebra and thinking about what you're doing, but you can get that the speed of light in this Hamiltonian goes as root the product of these two energy couplings, which is maybe not surprising, because if I rescale the whole thing, I expect the speed of light to get faster, right? And alpha is somehow the only dimensionless thing you can construct is the ratio, right? It turns out it's the square root of the ratio. Okay. But remember, at S is a half, gamma is infinity. So is the speed of light infinite? Is alpha infinite? Well, no. So this is a infinite renormalization, if you want, to get a finite alpha from an infinite, dumb guess. You need numerics to deal with it. So what do we do? How do we measure this? So first of all, let's look at alpha as this original definition, E squared over h bar c. the speed of light comes from the linear dispersion of energy with momentum, or you can do it in QMC. The speed of light can be measured in lots, and has been. It's actually part of, in the early work, seeing a transverse gapless mode with a linear dispersion and measuring its speed was part of how they said, look, this thing is actually realizing this Maxwell theory. Okay, so this speed was actually measured a long time ago, numerically. But how do you measure the E squared? So we could go and say, well, if I put 2 probe charges in, I know the energy is E squared over R. But the problem is I have to put it in a computational unit cell. And that has got huge finite size effects. I don't have a translation invariance. I've got a square. The dipole fields going through periodic boundary conditions do something completely crazy. You do Ewald summation, you rip your hair out. You're never going to get anything out of that, right? So what do? Well, don't use probe charges. And you think for a bit and you realize that in the ice manifold, the electric flux through periodic boundaries is actually topologically conserved. And so you can use that to probe the electric field produced by an elementary spinon without actually putting any spinons into your computation. Okay, so let me explain that a little bit. Here's, I guarantee to you that all those arrows, which I drew by hand, satisfy 2 in, 2 out. I hope. And this is proof by intimidation. Let me explain what I mean by electric flux sectors being topologically conserved. So let me flip that spin. Here's a Gedanken experiment. I'm going to create a charge and anti-charge, a spin-on and anti-spin-on. I'm going to move that spin-on through the system, through the periodic boundary. It's going to wiggle around for some reason. It goes back where it started and reannihilates. Okay, you see it left behind 1 extra unit of rightward going electric flux. Okay, but I can actually count that. So I can count through this vertical line how many arrows are going to the left, how many arrows are going to the right. Okay, or through the horizontal line, similarly, how many arrows are pointing up, how many arrows are pointing down. And I will get its an integer number. And what you see in this is that the number going to the right has clearly increased by 1 after my Gedanken experiment from what it was before. And if you count in this particular example, you get it's 1. The number going through this one is 0. And so we can define a set of quantum numbers, which are actually conserved by dynamics that never uses a spin-on. Because if I only do local dynamics, I can say reverse, by ring exchange, I can reverse these guys, but it won't change the total number going through this. Okay. Okay, so that's great. That means I have these extra boundary conditions I can put into my numerics and use translation invariant systems and weird sized computational cells. If my system is in a Maxwell phase, so in this electromagnetism, then when I go to the state, the ground state of the system with some amount of flux going through the wall, the electric field in that system will spread out uniformly. Okay, and so using that, I can actually estimate what the energy density should be, and I can measure the electric charge, basically by how much energy that boundary condition flux produces. Okay, so we do it. We divide. I literally measured alpha here by dividing E squared by HBAR C. Okay. This is based on constrained exact diagonalization on up to 96 spins of that ring exchange model. And we can extract the speed of light from the dispersion of the ground state energy with the momentum in the system and the E squared from the dependence of the energy on the electric flux through the boundaries. And we know that that's telling us about the fundamental charge because we increase it in units of a charge every time we increase the flux. Okay. Okay.
Why are there no small moments? Photons on the right?
Well, that's a sign of the biggest unit cell you can make in a 3D system with 96 spins, right? This is finite size limited 2 pi over. Yeah, it's the magnitude of K. So what did we do to try to make this a little bit more robust? This scatter looks big. It's actually visually deceptive. Most of the stuff is very close to the center, but all the dots are on top of each other. We're limited because we wanted to measure these energies. We did it with ED. 96, cubed root of 96 is actually not a very big number, right? That's the linear dimension of this box. So we just varied over as many different geometries as we could in that number of spins in order to see that they all basically agreed about what these quantities should be. And that's what that spread is from. And what you find is that alpha is about 0.1 for that pure ice model, pure ring exchange model. Okay. But actually, that pure model is just something I constructed for you guys to give this talk and make it simple, right? So the real system is going to have a more complicated, many more couplings, effective Hamiltonian, and we'll never be at this pure ring exchange point. Okay, we can hope that we are in the QED phase, but we'll never be right at that point. The main point is that as you add other kinds of things into the model and vary the couplings, you can move around in the QED phase. Alpha will vary, but this 0.1 is actually the right scale. This is the scale on which it varies. Okay, notice it's a factor of 10 bigger than the 1/137 of our universe, but that's the right scale. And to get it down to 1/137 is actually fine tuning. So if you realize any of these emergent spin ice type QEDs, you're in the phase, you just would guess that it's around 0.1 in this range, 0 to 0.2. There's no reason it should be close to a boundary. What's the 0.2? Well, certainly in all of our numerics, if we ever got alpha above 0.2, we found that we would go into an ordered state, which we interpreted for various reasons as being something to do with the B monopoles condensing, but that's hard to say that that's really the reason in the small sizes. This is actually consistent as an upper bound with a beautiful conjecture from John Carty from 40-some years ago, that there's a universal upper bound on alpha in a pure compact 4D lattice gauge theory of something like a quarter. The actual number is not known, but all the every numerical model people have studied have always found they can't drive alpha bigger than that.
What does the name upper bound mean?
It means that it's basically this. If your alpha gets big, that means your charges are strongly interacting. Your magnetic monopoles actually are weakly interacting. They interact as 1/alpha. And what happens in this compact gauge theory is that you can't get rid of the magnetic monopoles. I can send the charge gap away, but this thing always has those monopoles. And when they become sufficiently weakly interacting, they actually unbind. And that leads to condensation. And there's an upper. What's that?
Is it a quantum phase transition as you're varying alpha in the ground state? I mean, is that?
Well, alpha is, you can think of it, I think, like a marginal coupling. It's not I'm moving around a critical theory if you want. But once I hit, it's more like KT. So alpha is very much like the stiffness in KT. So it's like K, and in KT, KT Kosterlitz-Thales. And in Kosterlitz-Thales, there is an upper bound on the stiffness, or lower bound, depending on how you measure, beyond which it unbinds, and that's universal. And the Carty conjecture is that the same holds for the 4D gauge theory.
So it does not depend on the energy, the mass gap of the B monopole.
It does not depend on the mass gap of the B monopole. That is much less clear for this theory than it is for 2D XY. And that's why this is a conjecture. It's a beautiful paper. And actually, when we discovered this, it's a much forgotten paper. I emailed him about it and asked if he still thought it was right, because there's very little follow-up work. And he said, yeah. So, okay. Okay, so great. So that's the scale. So we have this, alpha is 0.1. Is it big? Is it small? Well, it's a lot bigger than our universe. It's still a small number in the sense that probably perturbative calculations are not crazy if you want to see, what this theory is going to do. And so in part 3, what I want to tell you about is what are some of the consequences that may actually be experimentally relevant, sort of signatures you could see that come from this interaction existing in quantum spin ice. Okay, so this is a cartoon of neutron scattering. The idea is that I'm a neutron coming in and hitting my pyrochlore material can flip a spin. flipping a spin, as we saw earlier, creates a spinon and antispinon on adjacent tetrahedra. And so it creates a spinon-antispinon pair. That's also called pair production. And that pair then carries away some amount of energy and momentum from the neutron. And the scattered neutron will therefore have a spectrum of, which will reflect the states of the spinon-antispinon pair that can absorb a particular energy and momentum. Okay, so I can probe pair production through the neutron scattering spectrum.
I don't want to get short on time, but it feels like at that point the spin S plus, and whether S plus or minus is just the effective two-level system spin or actual spin for the neutron interaction, it would matter. So,
it matters certainly. Yeah, it matters but at the level of form factors.
Okay.
Yeah. So there's a, see that twiddle?
Yeah.
There's a number there.
Okay. No, but it's not an issue like fractionalization. It doesn't change the power. Like it does. It's not like it couples to S plus squared or two neutrons are needed to couple to S plus or something like that.
No.
Okay.
No. That's right. Okay, good. So in order to understand what we should see if the neutrons scatter and produce pairs, let's just think quickly about some kinematics. So I have this photon, that's what we discussed a bit earlier, is linearly dispersing mode. It has some speed of light, which is small because it came in perturbatively in ring exchange. I had a relatively large gap to those spinons, which was set by the original ZZ coupling in my model. I'm calling it delta now. And then I didn't discuss it, but these spinons can move just by spin flips. And so that J plus, that term I added, which was the thing which I perturbed in to get down to here, actually directly moves spinons around. So that basically sets the inverse mass of the spinons. Okay, sets their bandwidth. This theory is not Lorentz invariant. The speed of light is small. The spinons can go fast. What that means, for example, is that the group velocity here, the slope of this thing, matches this slope at some finite momentum. Okay. Also, as I pointed out, we expect alpha to be around 0.1, so these interactions should matter. Okay. But before they matter, let's see what we should expect when they don't. So what you would expect if they were non-interacting particles is that I produce a pair. It costs me 2 delta to do it. I share that total center mass momentum Q with 2 particles, right? And so the threshold to do it would be something like 2 delta plus Q squared over total mass. And then the density of states I can produce has to do with the number of states available for 2 particles in 3D to share that relative momentum and make the total energy. And that gives you a gap, which with momentum, a gap delta, which increases quadratically to producing any response, any absorption. And if you go up like this, you'd be making a line cut, which is basically a 3D density of states. So it increases like a square root. Okay. Good. But lots of stuff can happen. Now, wait, how much time do I have? Am I negative already?
I think we started a little late, so I would say about 10 minutes.
Okay, 10 minutes, fine. Then I'll just say a couple words. I'll skip some of the details here. So actually, there's all kinds of stuff that happens because of the interactions. I'm doing pair production. So let's just think first about what happens when the center of mass momentum is 0. So that means, right, I'm creating these pair and they're flying directly apart from each other inside the system. Okay, so if I'm not at too high energy, I can neglect radiation. And this is the little a radiation, the emergent radiation in this. And if I do that, I have that there's a Hamiltonian governing, whoa, wrong. Man, I keep hitting the wrong button. A Hamiltonian governing these 2 particles, effective Hamiltonian, which is a free part, a Coulomb part, because they're interacting with a photon and, you know, it's just like QED. And then some short range stuff. This is lattice scale UV stuff, okay? And those interactions actually matter in this pair production of scattering. So rather than take you through any of the diagrams and stuff that allow you to to compute anything about this and the arguments, let me just say, if you think about what excitons are in semiconductors, it's very analogous. If I have a photon come into a semiconductor, which produces a particle hole pair, electron hole pair, they attract with Coulomb and also have some short range stuff potentially. And indeed, you expect that there are bound states, that's an exciton, and also a modification of how the continuous part of the spectrum turns on, okay? Those have names. That's a Rydberg bound state. This enhancement of the spectrum is called the Sommerfeld enhancement of the ionized states. And we expect that to happen in this system now because the interactions are non-trivial. Something which doesn't happen in the semiconductor analog, which I'll just mention briefly, is that we can probe at finite center mass momentum, whereas the photon always comes in with effectively zero momentum in the semiconductor. And so we now need to think about the problem where we have two particles that are moving apart with, moving apart, but also have some parallel component of their motion. And so there can be current-current interactions, okay? Bright was the first person to quantize that interaction. Happy to tell anybody who's interested more about it some other in detail later. The main effect is that it reduces the long range attraction with the parallel amount of the motion. And so what we get is that there's a suppression of the absorption at finite Q relative to what it would be from the Sommerfeld enhancement, which is this one. This is some complicated expression. It's not that complicated, but here, let me point out a couple of things. Alpha is there, interactions matter. Q is there, measured in units of MC. MC is a small momentum because C is small. So this actually is something that is a measurable effect potentially, okay? Okay. And finally, maybe the coolest one or the simplest to explain is simply that because the spinons can go faster than the speed of light, they should produce these emergent transverse spin waves. And you can compute the lifetime that induces, the amount of radiation, which will lead to a softening of that edge of the production. And so you put that all together and you find that the simple picture, which was sort of this featureless parabola with a square root turn on everywhere, gets a lot of structure. So over here at large momenta, greater than 2mc, the whole thing gets blown out because essentially you're Cherenkov radiating. So your picture of a two particle final state isn't any good. You're producing two particles plus lots of emergent photons. Down here at Q equals 0, you potentially have Rydberg bound states. You have a much harder turn on up here, which has to do with that Sommerfeld enhancement. And as you go to finite momentum, this all essentially goes away in a way that you can compute as it goes into that Cherenkov threshold. Okay, so there's a lot more structure that you can look for in the neutron scattering data, actually.
Looks like there's a peak that moves down as you increase momentum.
This thing.
Yeah, right.
Yeah. So that's coming because you're transferring. Once you get above a certain energy at a given momentum, the spinons you're producing are above the Cherenkov threshold again. And so they're transferring spectral weight downward and you end up getting a peak. Whereas when you're down here, they're not moving that fast. And so that's what that is. I don't know how much to believe that peak. I mean, it's there when you compute this way, but I would be a little skeptical about it. Maybe it's real. I mean, it's pushing the effective theory pretty hard. Okay. Any questions about this? I mean, I just went through, well, you can see just by the number of names up there that it was a big swathe of 20th century.
Why there's only one line, just one S?
Oh, in principle, it's a Coulomb problem. It could have many, but I don't know. Actually, one way to understand it is that I didn't try to broaden this. I didn't have any intrinsic mechanism to do it, so I just put a line there, right? But then I could ask the question, well, there's more up here. There's in principle a full Rydberg spectrum, but the bound state spectrum of the Coulomb problem, because it's what, 1/n², something, it goes up to the ionization threshold. And then there's a continuous set of states above ionization as well. And once I have a finite resolution, those blur together completely. So you can just think of this as me blurring all the other ones together if you want. But that level of detail I didn't try to put on the picture. So I think, the thing to point out here, we think this is cool because it's sort of saying there's a lot of structure that potentially is measurable, that's beyond just saying there's a 2-particle broad thing, right? And what's the sharpest thing? It's that at 0 momentum, you have a very hard onset potentially with ripples. And at finite momentum, it washes away in a smooth way and eventually disappears because of this Cherenkov.
What are the numbers on your strength? The color, I assume that's some kind of dynamic or structural factor, but there are no numbers. So, I mean, whether it's measurable or not depends entirely on that. Right?
It measured. Well, no. Yes. Yeah. No. Yes and no. So yes, in the sense, obviously, if the overall number is too small, you can't say anything. Now they see 2-particle continua in some stuff, or they see. Let me say it this way: they see smooth blobs, right? So this is, in some sense, visible, right? The question is, can I see? I think it has more to do with how big is this region, which I have enhancement over, and can I see that there's a significant sort of gradient this way, right? That there's a hard.
Those are the important things. General structure is just conservation law, but what you pointed out. So what are the? I mean, how much do the numbers vary in this interesting part near the y-axis is the question.
Yeah. Well, so the you're basically enhancing by order.
Twice have given the, I now understand what those arrows have given them. All right.
Yeah.
I get it.
Okay. So.
I have a question related to what Jay actually asked.
Yeah.
In semiconductor, there are some states that are found, but
Yeah.
they're dark.
Yeah.
Some of them are optically bright, some of them are optically dark.
Uh-huh.
So these are neutron bright.
These.
Meaning that, do you have the right optical selection rule? Or?
Well, certainly the S state should be. Yeah, you're basically you're probing it with a local, pair production, and it's very local. So I suspect that's right. It's suppressed if you look at states where the probability for them to be on top of each other is 0, right? So that'll be a suppression that would be for anything except for the S states, right?
And that's accounted for you.
Well, I didn't really draw it in that level. That line is a line you could think of as being the ground Rydberg state, right? Actually, there's an interesting question now that you say it. I haven't thought about this at that level of detail in a while. This is a couple of years ago. Once I'm at finite momentum, actually the problem you need to solve because of the bright interaction is not even isotropic. So there's actually a bound state that as far as I know, the problem's not solved. We kind of worked it out here, put bounds on how it should go away as you sort of approximate analysis of that bright Hamiltonian, but you can't solve it exactly once you have that center of mass momentum coupled in. So you don't literally have the usual spherical symmetry of S, P, D, et cetera states. So actually how it works in detail may have structure, but you'll be dancing on the head of a very small pin, I think, if you sort it out, at least for near-term experiments.
What is the ball radius of the lattice space?
Are
they Frankel, like kind of exciton?
It depends on alpha. Yeah. I think they're pretty small, but I'd have to think about it.
I think all the quantities are in the theory. Alpha, M, C, everything in the theory.
Yeah.
So ball radius will vary according to that. I think that mapping the theory is, I think, exact modulo some constants is out.
Right.
So that's like just taking in and doing the
Yeah, it is. I probably even could have answered you right away like a year ago. I just haven't thought about this in a little bit, this particular set of results. Okay, so as I think basically out of time, I will simply flash the bonus, which I even labeled bonus because I knew that it would be pushing it, which is that.
Is that something you have to do because there's something for?
Bonus slide. No, actually, the funny thing is that co-author is not on this paper.
Oh, wow.
Yeah. Yeah. No. He's not involved with this. That's yeah. No. This was different. So, okay. Let me just say quickly. What's an axion? It's a weird pseudoscalar particle that was first proposed as a way to solve the strong CP problem. It's a candidate for dark matter. You guys have probably heard talks that involve axions in the context of dark matter. And there's also 10 years ago, say, proposals for how you can interpret certain antiferromagnetic fluctuations in topological insulators as dynamical axions in terms of the response. This is due to to Shang et al. In that 2010 paper, which has led to sort of a condensed matter set of work on dynamical axions. And what we have recently thought about is what would it mean to have an axion in quantum spin ice, and how would you get it? So again, it's certain antiferromagnetic excitations that would be coupled to now the internal or emergent E and B fields. And what's neat about this realization of an emergent axion, if you want, compared to the topological insulator one, which is the other condensed matter proposal, is that it's actually coupled to this full dynamics of the internal gauge fields as opposed to just probe fields. Okay, so let me not actually go through all this. I can tell you how to get it. For anybody who wants to know, I can tell you how to get the right kind of coexisting pseudoscalar order, and why we think it's not totally crazy, which is that you need two kinds of symmetry breaking P and T, and both of them exist in materials that are pyrochlores, though they don't exist in these same materials at the moment. But that's not my problem. And then what's sort of a neat result, once you say that you have an axion coupled into your internal electromagnetism, is you can go back to that neutron scattering. You can actually look in the non-spin flip channel of the neutron scattering, which in the normal case, I didn't talk about it, gives you in principle a direct access to probing the photon of the emergent QED. So that's this linearly dispersing mode. But if there is an axion in the system, because of that other antiferromagnetic order, then you also indirectly couple to it through this axion photon continuum, which is another two-particle continuum with certain detailed structure that you can compute. And it's what we did. What's kind of neat about this is that, okay, if you want to turn off all the buzzy language, you could say, what did we do? We have a kind of exotic quotation marks set of transverse spin waves, right? Which are coupled to a not particularly exotic symmetry breaking order, right? An antiferromagnetic order. But it's a kind of order which doesn't couple to neutrons. And so if you don't have the exotic spin waves hanging around, you don't see it at all. This continuum up here wouldn't appear, okay? So by having the exotic thing around, which is hanging out at very low energy, this photon mode is very slow, you actually can now see something because you can actually couple to the axion photon. Okay, so that's a very qualitative effect of having the coexisting QED with the antiferromagnetic order. Okay, so that was the bonus. I'm happy to tell anybody about it in much more detail. Obviously, that was not enough. So what did I hope I conveyed to you? Quantum spin ice is realizes a compact U1 gauge theory. This is my pretty picture for that. There's pyrochlore, and there's a Feynman diagram inside of it. the natural scale for alpha is large and tunable. Large 0.1 is large, is only large if you compare it to 1/137. But that means that these kinds of signatures down here are not ridiculously small. They're small by factors of a tenth instead of factors of a hundredth. And then, well, the bonus was now I've got another pretty picture of pyrochlore with staggering and breathing and other things I didn't tell you about, with an embedded Feynman diagram, which involves photon-photon axion coupling. And okay, thank you all for your attention.